In this video, I will ask you a question of great conceptual significance, and that's to find the row-reduced echelon forms of these two matrices. And in this matrix, I chose the numbers very carefully. And in this matrix, I chose the numbers arbitrarily, and that's a clue. So why do we calculate the row-reduced echelon form? Well, if it's the matrix on its own, it's typically to determine its null space. If it's in the context of a linear system, it's to also determine a particular solution. So here it would be for the sake of determining the null space. But what if the null space is already known for some reason? What would be the point of calculating the row-reduced echelon form? Well, from the practical point of view, none. What else is the row-reduced echelon form going to reveal to you? But there will be some great conceptual applications in thinking about situations where you know the relationship among the columns and you would still perform the row-reduced echelon form to do some auxiliary task. So I'm thinking of a very specific application, and when we come to that application, it'll click and you'll know exactly what I was talking about. So let's rather easily determine the row-reduced echelon forms for these matrices. And of course, we won't do it by Gaussian elimination, because with these matrices, no leading ones and no ways to get those leading ones by row switching, it's just not an attractive option. But fortunately, we don't need to do any Gaussian elimination at all, because we're able to determine, because I chose the numbers carefully in the first matrix and randomly in the second, those relationships rather easily. Let's see what those relationships are. Well, we could do all the work. And maybe there you could take a matrix similar to this and actually do the work of Gaussian elimination, just to see that what we're saying right now is right. But this is the case where you don't have to do any hard work. And of course, this situation does not arise in practice too often, except possibly on a test, where a professor would give you a matrix for which he or she easily knows the row-reduced echelon form, so they don't have to compute it, but they have you compute it. But if you know this trick, you can completely avoid all the hard work. So, after all is said and done, the first column will be a pivot column because it's not the zero column. So just imagine all the amount of work that would go into it. Really an incredible amount of work, lots of fractions, lots of difficult calculation, but after the dust settles, what you will see is 1, 0, 0, 0, because this is what the first pivot column always looks like. Let's look at the second column. Is it linearly independent from the first column? Yes, it is, because it's not its multiple. So after all the hard work, what will be left here is the second pivot column, which always looks like this. So there you go. We've already determined two columns in the row-reduced echelon form without doing any work, but just using our overall understanding of row-reduced echelon form and our insight into its purpose and ultimate goal. Let's look at the third column. Do you see any relationship? Well, I made it the sum of the first two. I made it the sum of the first two, so that relationship will be preserved in the row-reduced echelon form. That's the whole point of Gaussian elimination. And if its relationship to the first two columns is preserved by Gaussian elimination, then in the end, it will still be the sum of the first two columns. And what is the sum of the first two columns? Well, it's 1, 1, 0, 0. There you go. We now have three columns. What about this one? I made this column second minus first. So if it's second minus first in the original matrix, it'll continue to be second minus first in the eventual matrix. And second minus first is minus 1, 1, 0, 0. And what about the last column? Well, I believe I made it 10 times the first column plus the second column. So that relationship will be preserved, and it will still be 10 of the first column plus the second column, followed by two zeros, and there you go. This is the row-reduced echelon form, rather easily for a matrix for which Gaussian elimination would have been a nightmare. And after all of that hard work, you would still end up with this. Now, it's very rarely in practice that the ultimate question is, what is the row-reduced echelon form of this matrix? It's really a means to a greater end, like determining the null space or its dimension or something like that. So I just wanted to mention that. I'm not 100% sure what the relevance of that last statement is, but here we go. We skipped all the hard work and still have the row-reduced echelon form of the matrix. Okay, going to this matrix, as I mentioned, I chose the numbers rather arbitrarily. I just threw the numbers in without any pattern. So what does it mean in terms of the likelihood of these columns being linearly dependent? Well, that likelihood is very low. Remember our geometric analogy? Picking 3 vectors, throwing them up in the air, letting them tumble, and then catching them. And what are the chances that they all end up in the same plane, like this? 0. So the chances are the columns of this matrix are linearly independent. I can bet $100 on it, or even a lot more than that. So since the columns of this matrix are linearly independent, they will all be pivot columns in the row-reduced echelon form. So the first column, after all the hard work that we're skipping right now, will look like this. The second column will look like this. The third column will look like this. And the final column will look like this. So they're all pivot columns. All of the columns will have this familiar form. And this will be the row-reduced echelon form of this matrix, which for square matrices has a particularly attractive form because it's all zeros except the ones just running down what's called the diagonal. And this actually ends up being a very special matrix. For us, its significance is not at all obvious, but when we talk about matrix multiplication and develop matrix algebra, this matrix will have a very special property. And for that very special property, it is called the identity matrix. So the row-reduced echelon form for a square matrix with linearly independent columns and therefore linearly independent rows, remember the rank discussion, is the identity matrix. So there we go. This is not a common situation in practice where the relationship is known and you have to determine the row-reduced echelon form. It's usually the reverse. You determine the row-reduced echelon form in order to back out the relationships among the columns. But this understanding and this great insight into the row-reduced echelon form will prove to be of great benefit just a little bit later on.